I want to tell you about some work on looking for axions using compact stars. For this talk, compact stars is going to mean white dwarfs and neutron stars, and I'll tell you about projects that involve both white dwarfs and neutron stars, although you see the physics is quite similar. And these searches are going to revolve around X-ray telescopes. But before I tell you about the specific projects that I have in mind, I want to start just by taking one step back and getting everyone on the same page by reminding you about some of the theoretical motivations and observational motivations for the axion. So I'm going to be talking today about the QCD axion and axion-like particles, and I'll tell you what the difference is, but let me start with the QCD axion. The QCD axion was originally introduced to solve the strong CP problem, which is the problem of no observed neutron electric dipole moment. So there's a fundamental parameter of nature called theta. If theta is non-zero, which is generic, the neutron would have an electric dipole moment, which would mean it would precess in the presence of electric fields, but no precession is observed. So we know that theta has to be very close to zero. In particular, we know it needs to be about 1 part in 10 billion away from zero. And you should keep in mind theta is an angle that would naturally go from minus pi to pi. And so the confusion of the strong CP problem is, why is this value so close to zero? So in the late 1970s, Petchy, Quint, and others proposed a solution to this problem where they noticed that when you randomly create a universe, so you draw a value of this theta parameter, it lies somewhere between minus pi and pi. It really looks like that value of theta wants to roll down to the origin, because the neutron would be in a lower energy configuration if it could dynamically evolve down to the origin. But of course, it doesn't make sense for theta to relax down to zero because it's a fundamental parameter of nature, like the electron mass. It doesn't make sense for it to change. So what they did, and others did, was to promote this theta to a dynamical field. That field is called the axion field. And now this field, since it's dynamical, it can evolve down and minimize its potential, thus dynamically solving the strong CP problem. So let me go through this at the level of equations now. So you should think of the axion, which I'll denote by A throughout this talk, as a pseudo-Goldstone boson of a symmetry called the Petchy-Q symmetry, which is broken at some high scale Fa. And then at low energies, you have this dimension 5 coupling of the axion to QCD with field strength G mu nu. And so it's dimension 5, so you have that mass scale Fa in the denominator. So theta bar here, that's that theta parameter. And now QCD induces this neutron electric dipole moment, which is proportional to this entire combination. But below the QCD confinement scale, QCD instantons generate a potential for the axion, which looks like this quadratic potential. And now when the axion dynamically minimizes potential, as I said before, it dynamically removes that neutron electric dipole moment, thus solving the strong CP problem. In the process, the axion acquires a potential. So it's no longer a Goldstone boson of that Petchy-Q symmetry. It's now a pseudo-Goldstone boson because we've explicitly violated that symmetry. So if we expand out this potential, we end up with a small axion mass, which is inversely proportional to this decay constant. So for a reference scale of, say, 10 to the 12 GeV, we end up with a mass on the order of 10 micro eV. Very importantly for this talk, perhaps most importantly, axions also couple to electromagnetism through a term that's very similar. It's a dimension 5 operator, AFF tilde, where F is the QED field strength. And there's a dimension full coupling, G gamma gamma. This looks like AE dot B if you expand it out in terms of electric and magnetic fields. And G gamma gamma is inversely proportional to the decay constant Fa, but there can be some model dependence which enters into the numerator. Also important for this talk, axions, in addition to coupling to electromagnetism, they're also expected to couple to matter, to fermions, to standard model of fermions, through these axial type coupling, where you have a derivative of the axion coupled to this axial current. Here, I've just written the flavor diagonal couplings. You can also have flavor changing interactions in principle. And you have, again, this is dimension 5, so you have this scale Fa in the denominator. It is convenient, and I'll just use this.
Well, that's great. Okay.
Hi, no worries.
I know exactly what just happened. A fun physics experiment. I don't have very sophisticated Wi-Fi, and someone turned on the microwave in my house, and that killed the Wi-Fi. So microwave is now off. And hopefully that'll solve the problem for the rest of this talk. Okay, can everyone hear me again?
Yeah.
Yes.
Good. Okay, so let me keep on going here. One point I just want to stress, because I'll mention this later on in my talk, you can have both, generically you would expect to have an ultraviolet contribution to this axion-fermion coupling. And this happens, for example, in QCD axion models, where your standard model fermions are charged under this PQ symmetry. But even if you don't have order 1 contributions to this coupling in the UV, you would expect to have contributions in the infrared, because this operator is generated under the renormalization group. Although the loop-induced couplings at 1 loop tend to be much smaller. Well, they're smaller than order 1 because they're loop-induced. And it depends on exactly how you couple to SU2 versus U1. If in the infrared we only measure the coupling to photons, then we don't know a priori what fraction of that is coming from our coupling to SU2 versus what fraction is coming from U1. And there's some small difference numerically in the loop-induced contributions depending on what you couple to. Okay, so everything I've said so far is for QCD axion. Let me contrast that with axion-like particles. So remember, our QCD axion is going to couple to QCD, to electromagnetism, and to fermions. We could also have some small bare mass, some small other explicit violation of the PET-GQ symmetry. But in order for the QCD to be a good solution to the strong CP problem, the QCD-induced mass needs to be much bigger than this bare mass. So an axion-like particle, at least for the purpose of this talk, is going to be exactly like the QCD axion, but is not going to have this coupling to QCD. So we'll have couplings to electromagnetism, we'll have couplings to fermions, but we're not going to have, and we'll have these bare masses, but we'll not have this QCD axion coupling. So this picture of axion-like particles as a motivation emerges in this idea of the string axiverse, where you find a large number, say n, pseudoscalars, ultralight pseudoscalars, which will generically couple to everything, including QCD. But the linear combination, which couples to QCD, is going to get a mass from QCD instantons, and that'll become the QCD axion eigenstate. So that'll have a large mass. And then we're left with these n-1 alps, which will, by construction, not couple to QCD, but can still exist within the spectrum of nature. And I think it's very interesting and motivated to try to look for those particles too. So that's all I want to say about the axion at a particle level. A few years after the axion was introduced, it was realized that axions could explain the dark matter of the universe. I'll explain that to you now. And then axion-like particles in kind of the preceding decades started to become more and more popular as well. And today I'll really be focusing on ideas going on now to try to detect these particles if they exist. So first, let me say a few words about axions as dark matter. So first, the language that we use when we talk about axions as dark matter is very different from the language we use when we talk, for example, about WIMPs as dark matter. And the reason is that axions just have a really small mass. So what we measure in astrophysics with dark matter is the amount of stuff, the amount of mass within some fixed volume. So as we make the mass of the individual particles smaller and smaller, we simply need more particles to make up that fixed total mass. Those particles come closer and closer together. Axions are bosons, so their wave functions begin to overlap. We have high occupancy numbers for each quantum state, and we transition from the quantum description to the classical description. So when we talk about axions as dark matter, we use the language of classical waves. So now we have this new classical field, which I'll call A, and we need to include it in the equations of motion in the expanding universe if we want to understand its cosmological abundance. So this is the homogeneous equation of motion, where I've linearized the equations of motion. So H here is Hubble, which is temperature squared over m Planck in the early universe. I can solve this in real time at high temperatures, because at high temperatures, Hubble will dominate over the mass term. Everything has a time derivative, and one solution is simply A equals a constant. So if I plot this solution, A is a function of time or inverse temperature, it starts out frozen at its so-called initial misalignment angle until Hubble drops the mass, after which point the field begins to oscillate and behaves like a damped harmonic oscillator, oscillating at the frequency of the axion mass. And it turns out that after this point, the coherent fluctuations of the axion field behave like cold dark matter for astrophysical purposes. That doesn't mean that you've generated the correct abundance of dark matter. You have to carry out the calculation in order to check that. And you get the correct abundance of dark matter for an order 1 initial misalignment angle for a decay constant on the order of 10 to the 12 GeV. Okay, so with that said, this is the space that we're going to live in throughout the rest of this talk. So here is the axion-photon coupling on the y-axis as a function of the axion mass on the x-axis. So this is this operator which couples the axion to electromagnetism. For the QCD axion, G gamma gamma is proportional to the mass. So up to model dependence, for the QCD axion, you expect to live within this gold band. So the first thing, just to orient you, I just told you about this story about QCD axion being dark matter. So I'll call it just right dark matter when you happen to live somewhere near this blue box, because that's where you have these decay constants on the order of 10 to the 12 GeV, and it seems very easy to produce the correct abundance of dark matter. If you follow that picture I was describing on the last slide, you'll see as I go to higher Fa or smaller masses, you naively produce too much dark matter. So you're gonna have to do something to get the correct abundance of dark matter. I'm putting too much here in quotation marks because it's very easy to get around this. I don't want to go through the ways that you can get around this, but it's very easy to get around this, this naive problem of producing too much dark matter as you go to smaller masses. Similarly, as you go to higher masses, you naively don't produce enough dark matter, although you can also get around that too. So you can have QCD axion dark matter, which lives throughout this whole gold band. So everything which is in some color is one constraint or another from my group over the past few years. I just want to, this is an aside from my talk, but I think it's exciting, so I want to mention it, what's going on with the abracadabra experiment. So let me just take a quick aside and tell you about some updates. This is an experiment that my collaborators and I proposed a few years back. It's now a real experiment in the basement at MIT. We look for axion dark matter in the laboratory. We just had some new results that came out this year, which improved our sensitivity by a little bit, got us close to the cast limit. But the really exciting thing about this program that I just want to quickly mention is that we scale very well with volume. And we teamed up with the DM radio collaboration at SLAC, and we received some preliminary funding from the US Department of Energy, and we're expanding out to a 50-liter version, which should have sensitivity something like what I'm showing here. We're also planning for a meter-cubed experiment, which will probe the QCD axion. And then our ultimate goal is a multimeter experiment, which we call GUT, which would be able to probe QCD axion dark matter with decay constants on the scale of grand unification. So this is super interesting, very motivated parameter space, and hopefully we actually get there over the next few years. But for this talk, I'm not going to be focusing on getting after this parameter space down here at the QCD axion. I'm mostly going to be focused on this part of the parameter space, ultra low masses, and coupling slightly below current limits, and trying to get after these axion-like particles, which are motivated in part from thinking about string theory type scenarios. And one thing I just want to stress is that naively, you don't produce enough dark matter up here. So if you're an ALP and you're above this red line, it's very hard to explain the dark matter abundance. So in order to take a search seriously for axions, including abracadabra, but in order to take a generic search for axions seriously that lives above this red line, I think it's very important for that search to not require the axion to be a sizable component of the dark matter. And so in this talk today, we're going to be discussing searches that make no assumption about the dark matter nature of that particle. So this talk is going to be focusing, roughly speaking, on this blue region here, trying to push down even incrementally below current constraints. And again, I think this is very motivated parameter space. I'll give you one example. In some explicit string constructions, people have found, for example, Halverson et al., that the typical axion-photon coupling will be quite small, will be somewhere down here. But since you have a large number of ALPs, one of them might fluctuate up and have a larger axion-photon coupling and might sit roughly within these, the range of this orange arrow. So this is a range of parameter space that we actually have a chance of detecting. Okay, so with that said, here's an outline for the remainder of my talk. I'm now transitioning to my work. So I'm going to begin by overviewing the theory of X-ray observations of white dwarfs and neutron stars as probes of axions. I'll be talking about white dwarfs and neutron stars at the same time because the theory is very parallel. I'm then going to go on to tell you about the actual results from our data analyses and our observational campaigns. So I'll tell you about X-ray data analyses of neutron stars in the Magnificent 7 X-ray anomaly. And then I'll then tell you about some very recent data that we took towards a white dwarf, RHJ 0317. And then I'll conclude by telling you about some future work that we're working on and some future work that I would just like to see happen. So I should say that all of these bullet points relate to this following set of works. There's one very common name here, which is my grad student, Chris Desert, who deserves a lot of credit for the work that he's done on these papers. Okay, so with that said, here's the idea that's going to kind of govern the rest of this talk. So the idea is that if axions exist within the spectrum of nature, again, they don't need to be dark matter. They can be produced inside of neutron stars or white dwarfs. Here's the neutron star case, where you have neutron stars consist of degenerate nuclear matter, so degenerate neutrons in particular. They can have two neutrons scatter off of each other by exchanging a pion, brim off an axion in the final state. That axion is weakly interacting. It escapes the neutron star. It then can hit the strong magnetic field surrounding the neutron star, convert to a photon. The processes which govern the scattering are thermal processes. So the energy of this photon is going to be of order the core temperature of the neutron star, which might be of order a few keV. So these photons will be in the X-ray band, so we can look for this with X-ray telescopes. So immediately we can understand that the luminosity in X-rays is going to be proportional to the axion-nucleon coupling squared and the axion-photon coupling squared. And this is kind of like a very fancy light shining through walls experiment. And the reason is that the temperature of a neutron star, the core temperature of a neutron star or a white dwarf, tends to be much hotter than the surface, which is very cool. So we can see with axions directly into the hot core. So if I plot the flux as a function of energy, the surface is very cool. So I might expect to see this thermal surface emission. A typical neutron star, at least the ones I'll be looking at, will have surface temperatures on the order of 100 eV. And then if I go to higher energies, I might expect to see a hard X-ray signal, which could come from axions. So let's look at this process in a little bit more detail. The luminosity radiated purely in axions for a typical neutron star is about 0.05 solar luminosities for an axion-nucleon coupling of order 10 to the minus 10. Remember, this is dimensionless because you have the mass of the nucleon in the numerator. One point I just want to point out is this fast core temperature scaling. This scales like the core temperature to the 6th power. I don't have time to derive this formula, but I will explain the TC to the 6th scaling here. But just to reiterate, the spectrum of axions which comes from this process is going to be roughly thermal. Core temperature is typically about 10 keV for the neutron stars I'll be looking at, whereas the surface temperature is much lower. So let's at least understand the scale in TC to the 6. So one thing which makes this process extremely frustrated, it would be much more efficient, but something, and that but is that the neutrons are degenerate inside of the neutron star. And there's a very high Fermi momentum on the order of 0.3 GeV, which is much higher than the core temperature, which is on the order of 10 keV. And these neutrons need to scatter into free states. And that essentially means that they need to be living within a core temperature of the Fermi surface. So that brings in a phase space suppression factor, which just scales like the area of that Fermi surface. And there's two neutrons in this scattering. So you get a Fermi suppression on each of them. Each of their Fermi suppression scales like TC squared, but in total you get a TC to the 4th factor from this double neutron degeneracy. The cross section scales like temperature, essentially associated with that spin flip associated with emitting the axion. And then we're calculating a luminosity. So we need to have a cross section and multiply it by the energy of the outgoing axion. So in total, we have 1, 2, 6 factors of TC, which enter into this luminosity. However, this can be much more complicated. So one of the complications which enters into here is the onset of nucleon superfluidity. So neutrons inside of a neutron star can become superfluid, protons can become superconducting. And when you have a superfluid or a superconductor, you suppress scattering. That's what it means to be a superfluid, essentially, is to have suppressed scattering. And so you begin to exponentially suppress this Bremsstrahlung rate when the temperature drops below the superfluid transition temperature, which is on the order of a few times 10 to 8 Kelvin, on the order of the temperatures that we care about. Although this superfluid transition temperature is a strong function of density, which is also a function of your equation of state, which is also unknown for neutron stars. So there are many unknowns which enter into this process. Unfortunately, those unknowns enter into the exponent of an exponential suppression. But it gets even more complicated than that, because superfluidity, while it suppresses the Bremsstrahlung rate, it opens up a new channel for producing axions, whereby you form or break a Cooper pair and emit an axion in the process. And that Cooper pair breaking information channel can outshine the Bremsstrahlung channel, depending on temperature and superfluid transition temperatures. So that's just to say there's a lot of theoretical uncertainty which goes into the calculation of this axion luminosity. By contrast, the white dwarf channel is pretty simple. The picture that I think you should keep in mind, the picture that I have when I think about this, is that the white dwarf search is kind of ultra clean. As I'll show you, it's cleaner both theoretically and is cleaner observationally. The neutron star search is messy. With that mess comes a lot of potential. There's a lot of potential to produce a lot of axions. There's a lot of potential to see things in data, but there's also potential to be off and to be confused. So it's good to have both of these different search channels. So inside of the white dwarf, you produce axions predominantly from a very similar process where you scatter an electron off of an ion by exchanging a photon, and then you brem off an axion in the final state. So in this case, the luminosity of axions involves the axion-electron coupling. The core temperature of the white dwarf that we'll be looking at will be of order of 1 keV. The surface temperature is actually much lower than the surface temperature of a neutron star. It's in the visible, on the order of a few eV. Notice this only scales that core temperature to the 4th power, and that's because only the electrons are degenerate inside of a white dwarf. The electrons are scattering off of non-degenerate ions, so the ions don't have that extra degeneracy factor. There are additional complications in the white dwarf case, although you can account for them more precisely. One additional complication is the fact that your ion is not sitting there in isolation, but you have to account for ionic correlation effects, or the fact that that ion is interacting with the rest of the ions around it when you're exchanging momentum. So for example, at very high densities, you can form a lattice of ions, and then you need to account for the fact that your electron is scattering off of a lattice. So when you account for all of this, the differential emissivity, which is the fact that the quantity we care about, which is the energy in axions emitted per cubic centimeter per second per keV. This has an alpha E and M squared from the fact that this is an electromagnetic process, axion-electron coupling squared, a thermal factor because it's just a thermal spectrum of axions we're emitting. Then we sum over all ionic species. We have the atomic number we're scattering off of, since it's squared, since it's an electromagnetic scattering process, the number density of ions that we're scattering off of. And then there's this dimensionless factor F, which we've defined here, which accounts for all of this, these ionic correlation effects. And so roughly speaking, if this F was 1, you would just be scattering off of an ion in isolation, but deviations of this F from 1 account for the ionic effects. So I'm plotting F here as a function of radius in a white dwarf. Radius is plotted as a function of the enclosed mass, so the integral of mass out to that radius. So at very low radii, this is for a few different ions present in the white dwarf, carbon, oxygen, neon, for example. This F, so at low masses, the density is very high, the ionic correlation effects are very strong, and you can see that we suppress our rate by maybe a factor of 5 compared to the naive expectation. Okay, so now we know how to produce our axions. The next thing we need to do is we need to figure out how we're going to convert these axions into photons. So our axions have now made it out of the star, and they want to be converted in the magnetic field. So the axion photon conversion process is made complicated by strong field QED. in particular the Euler-Heisenberg Lagrangian, which comes from integrating out the electron. So this is a nonlinear correction to Maxwell's equations. And this nonlinear correction to Maxwell's equations, it changes the dispersion relation for the photon depending on the polarization direction. So in the presence of the Euler-Heisenberg Lagrangian, you can derive the mixing equations for the axion and the photon. A here is again the axion, little a. Big A parallel is the component of the vector potential polarized parallel to the magnetic field direction. So in a WKB approximation where you say that the mixing is taking place over a distance much larger than the wavelength of the photon, you can reduce the naively second order mixing equations to first order Schrödinger type mixing equations, which is what I'm showing you here, where there's a mixing Hamiltonian. So you should think of this matrix as the mixing Hamiltonian. The important part is the off diagonal part, this delta B. This delta B is proportional to the axion photon coupling and the strength of the magnetic field. And this delta B is the part which tries to rotate the axion into the photon. So this induces mixing. However, you have these terms on the diagonal which suppress mixing. The delta A is simply the axion mass term, where Ma is the mass of the axion. And the delta Euler-Heisenberg is an effective mass term for the photon, which comes from the Euler-Heisenberg Lagrangian. So it becomes more important at stronger magnetic field values. So you can solve this mixing equation for a dipole magnetic field, which is what we're going to assume for neutron stars and white dwarfs. And you find the following formula for the conversion probability, where the conversion probability is about 10 to the minus 4 for an axion photon coupling on the order of 10 to the minus 11 inverse GeV for a typical neutron star value. So magnetic field on the order of 10 to the 13 Gauss, a size of the neutron star on the order of 10 to 10 kilometers. But one point which is very interesting is the scaling with magnetic field is extremely small. It's b to the 2/5. Naively, you might have said this should scale like b squared if you're used to, for example, thinking about past. But the reason it scales so slowly with magnetic field is that the Euler-Heisenberg term suppresses mixing and becomes more important at larger magnetic fields. So you have a competition between this term and the one which induces mixing. So this is interesting because it turns out a white dwarf is actually better at converting axions to photons than a neutron star. So for a typical neutron star, as I said, you'd have a conversion probability on the order of 10 to the minus 4. For a typical magnetic white dwarf, which has a magnetic field on the order of a few hundred megagauss, your conversion probability would be quite substantially larger. And that may be surprising because the magnetic field, which is the first thing you think about, is smaller for the magnetic white dwarf, quite a bit smaller compared to the neutron star. However, a neutron star is about 10 kilometers and a white dwarf is about the size of the Earth, and you just win more by having a bigger object than you do by having a bigger magnetic field. So when you put this all together, the white dwarfs and the neutron stars, they probe different couplings. The neutron star probes a nucleon coupling. The white dwarf probes the electron coupling, but they turn out to be about equal probes, about equal strengths. You win more on the neutron star side on production, but you lose on conversion, and it all roughly evens out. So then with that said, I want to go through and tell you a little bit about data towards both of these types of systems. I'll start with the neutron star story, and then I'll move on to tell you about the white dwarfs. So the first place, we realized that both neutron stars and white dwarfs were very good places to look for this process at the same time. But we couldn't look at white dwarfs at the time because the surface temperature of a white dwarf is on the order of an EV, which means that white dwarfs typically don't extend up into the X-ray band. So there is no relevant X-ray data to look at. However, neutron stars with temperatures on the order of 100 EV, their surface emission will extend up into the soft X-ray band, which means there is an abundance of X-ray data to look at, archival, towards perfect neutron star targets, but people had only ever looked at the low energy part of the X-ray data. So, they collect data from a few hundred EV up to a 10 keV, but they just never had looked at the data above a keV. So we took all of this existing X-ray data and looked at it at higher energies. We focused on 7 neutron stars called the Magnificent 7. They're about 100 to 500 parsec from the sun, which makes them relatively close. They were discovered in soft X-rays with the Full Sky Rosat X-ray survey. From spin down, they're known to have large magnetic fields on the order of 10 to 13 Gauss. Their surface temperatures are about 100 EV. And previous to our work, no non-thermal emission had ever been detected from these neutron stars. And they were all pretty old and isolated. They were thought to be very boring, just sitting there, essentially radiating as perfect black bodies. So we used archival data from the Chandra telescope and the XMM-Newton telescope. We used data from 2 to 8 keV. Again, that data in some cases had been sitting there for decades, but as far as we are aware, it had never been looked at. Only the part below 1 keV had been looked at previously. There are a lot of details here which aren't super important, but a few that are. XMM-Newton has 2 cameras on board which are independent. One is called PN, the other is called MOS. And Chandra, relative to XMM-Newton, has much better angular resolution. So what we saw when we looked at these neutron stars was something very surprising. We saw an excess of hard X-ray emission emanating from many of these magnificent 7. So that's what I'm showing you here for J1856, which is the neutron star with the brightest X-ray, hard X-ray excess. So we can see at low energies, this is flux is a function of energy, is that thermal surface emission dropping down essentially exponentially. And then at larger energies, we saw this excess hard X-ray emission. We saw this from all 3 cameras that we used to look at this neutron star. And so the question that we wanted to ask was, could this be coming from axions? So first, you can compare the spectral shape to the axion model prediction. So on the y-axis is again the spectrum as a function of energy, but I'm just concentrating on hard X-rays, so on high X-ray energies. And you can see the axion model prediction roughly follows that. You would expect the data, although maybe that's not the most constraining statement. The other question you might ask is this X-ray emission actually coming from the location of the neutron star? So here we make use of Chandra, which has that good angular resolution. And we can see this is a map of the photon counts, and we can see the photon counts are indeed coming from the location of that neutron star. And the other thing I should just mention is there's no obvious astrophysical explanation for what's going on here. That doesn't mean that one doesn't exist, but one hasn't been thought of yet. So then we can look at the other magnificent 7, because there's 7 of them. Here's 1856. And what I'm showing you in green and gold are the 1 and 2 sigma confidence intervals for the intensity that we measured in hard X-rays. And so you can see in 1, 2, 3, 4 of these magnificent 7, we measure hard X-ray excesses in more than 2 sigma. And then a few of these, another 2 are consistent, are non-zero at 1 sigma. One of them is consistent at 1 sigma with 0. And in black is the best fit axion model prediction. So you can see that the black points, which are the model prediction, are following the trend of the data, which is interesting and might make you want to make a plot like this, which is the interpretation of this magnificent 7 excess in the context of the axion model parameters, in particular, the axion photon times the axion nucleon coupling on the y-axis as a function of the axion mass. And the best fit parameter space does extend a little bit below current constraints, which come from combining CAS limits with cooling limits from supernova 1987A. And so maybe an axion is explaining this excess and is sitting in this parameter space. So that's very exciting, but I want to pause for a second, tell you a different story, and then I'm going to come back to this story at the very end of my talk. So let's hold this story for a second. Just remember this. We have this excess here, which looks very promising. And now I'm going to change gears a little bit, tell you about this white dwarf search, because I think it does shed some light on what could be going on in the neutron stars. So now let me tell you about this recent work on looking for the same process, but not in neutron stars, instead in white dwarfs. So it was New Year's 2021, just a few months ago. New Year's 2021 was not as any of us hoped or imagined New Year's 2021 would be. So we finally got our long-awaited holiday present, which was dedicated data from Chandra towards this magnetic white dwarf. This data was supposed to be taken much earlier in the year in 2020, but it was postponed because of the pandemic. We finally got word around Christmas time that our observation was going to take place. It took place, and we got the data right after New Year's. And we were extremely excited to open it up and to see what was there, because we knew about this hard X-ray excess, And we are getting ready to see what happened in this ultra clean white dwarf search. And I just want to stress that I think these white dwarfs are ultra clean. The surface emission is at much lower energies. It's on the order of a few eV. So there's a big separation in energy between the surface emission and the axion-induced emission, which is still in the X-ray band. So relative to the neutron stars, there's more separation between astrophysics and new physics. So we chose this one white dwarf, REJ0317, because it's the hottest magnetic white dwarf known. It has a surface temperature on the order of 5 eV, which translates to expected high core temperature, which enhances our luminosity. It's also one of the closest magnetic white dwarfs at about 30 parsec away from the sun. That distance has so many digits because it's measured very precisely with Gaia parallax. Their surface magnetic field is about 500 megagauss, and I'll tell you how that surface magnetic field is measured on the next slide. Its core temperature, if you translate this, is about 1.5 keV, and I'll tell you more about the measurement to that core temperature also. And just to stress the point, there was no archival X-ray data, relevant archival X-ray data to point to, so we had to go out and collect this data ourselves. So let me just tell you a little bit about how the magnetic field is measured, because it's quite cool. It's measured from the fact that there's hydrogen in the atmosphere, and you can use Zeeman splitting, which just becomes abundantly clear when you have magnetic fields this high. So this particular white dwarf has a period of a few hundred seconds, and here you're seeing different phases throughout its rotation period. And you can see these absorption lines as a function of wavelength, and look at how these absorption lines change as you go through the phase of the white dwarf. So these are Zeeman splittings. And from looking at these Zeeman splittings, their form, their width, and exactly how the lines are split across the full spectrum of the Balmer series, you can essentially reconstruct the surface magnetic field profile on the surface of that white dwarf, which is what's being shown here. So you can see that the magnetic field oscillates between about 900 megagauss at one of the poles down to about 100 megagauss at the minimum. So this is one way of measuring magnetic fields, which is very precise. There's another way of measuring the magnetic fields, which is completely independent by using optical data and looking at circular polarization. And they agree quite precisely on the strength of the magnetic field. So in our analysis, we are averaging over many rotation periods, and we simply assume a dipole of 200 megagauss strength. This turns out to be conservative with respect to more realistic models, but the dependence on B is very small for the reasons that I told you about previously. So the next question is, how do we know the core temperature of this white dwarf? So we again use Gaia data. We use Gaia luminosity data. So Gaia has measured the color and the magnitude of the star. So here I'm showing you the color on the x-axis, the magnitude on the y-axis. The data point is the star, is the Gaia data. And we compare this to dedicated white dwarf cooling sequences that predict for different white dwarf masses and different white dwarf temperatures or a function of time, they predict the Gaia magnitudes and colors. And so you can see for 3 different mass white dwarfs, these cooling sequences. So here, this green one turns out to be one of the best fit ones. As we go down in time, the white dwarf cools. And then to be consistent with the data, we need to be living somewhere in here, from which we can read off the core temperature, which is what's shown here on the x-axis. This is just the fit, delta chi squared. And you can see our best fit 1 sigma, 2 sigma core temperature. For our fiducial analysis, we take the core temperature to be at the lower 1 sigma end of the 1 sigma confidence interval. Although you can see the dependence in red on the axion luminosity on this core temperature is quite small over this temperature range. So the red is just showing you how the axion luminosity changes the function of temperature. So we make a conservative assumption, but it doesn't really make any difference at the end of the day. Also, again, there's a completely independent way of measuring the core temperature, and that is by using the fact that white dwarfs cool in a very predictable way as a function of time. And this white dwarf happens to be in a binary, and its binary companion has a well-measured age. And if you assume that these 2 stars were born at about the same time, you can only use the binary as age to then infer the core temperature of the white dwarf, and you get almost the same core temperature, or at least the same core temperature up to uncertainties. So we're pretty confident that the core temperature is about 1.4 keV. Okay, so then the data. We had 40 kiloseconds of dedicated Chandra data. And we looked at this data between 1 to 9 keV. And we saw absolutely nothing. So I would be lying if I said this wasn't a huge disappointment. You know, we were hoping to see a big excess at the center of this image, and that's not what happened. That's not how the science went. We saw absolutely nothing. So here I'm showing you an image of the counts. So the different pixels here are show you where photons hit the detector, and the colors show you the energy. This black point in the middle is the location of the magnetic white dwarf. You would expect a signal to be spread out by the instrument angular resolution, but that's quite small. The signal template is showing you that angular resolution. These red points show you intermediate points in the calibration process, coming from the fact that, for example, the white dwarf is moving, so we need to account for where it was on the specific date. But we believe we've done that properly. We're looking at the right part of the sky, and so we can conclude that there were no X-rays coming from this magnetic white dwarf. So we can then go ahead and set upper limits. So here I'm showing you the spectrum as the function of energy. In black are the data, which are just upper limits because we didn't observe anything. And in red, I'm showing you the predicted model prediction for an axion with a specific combination of couplings, which is a decay constant on the order of a few times 10 to the 9 GeV. So our limit ends up being this particular combination less than about 1.3 times 10 to the minus 25 inverse GeV and 95% confidence, assuming a very low axion mass. If you plot this in the plane of axion electron times axion photon couplings, we exclude all of this parameter space in red. So we improve upon current constraints beyond the white dwarf cooling constraints and beyond other astrophysical constraints in the axion photon coupling, putting into farther tension some existing stellar cooling anomalies interpreted in the context of axions. I find that plot to be not super useful, to be honest. So let me show you this plot, which I think I have much more intuition for, and so maybe you will have more intuition for. This is just the plot that I'm used to looking at, which is the plot of the axion photon coupling. So G gamma gamma is a function of axion mass. In order to put our limit on this plot, we need to make an assumption about the axion electron versus axion photon coupling. And so we have to invoke some level of model dependence, because what we measure is a combination of the axion electron coupling times the axion photon coupling. And here I'm only showing you the axion photon coupling. So I'll make two assumptions here. One, I'll assume I have a tree level coupling to electrons. So I can assume my dimensionless number coupling my axion to electrons is the same as axion to photons. In that case, you can understand just how crazy strong this limit is. This cuts orders of magnitude into new parameter space and excludes, for this particular ultraviolet completion, everything above this dash red curve. The shape of this curve at high masses comes from the fact that as you go to high masses, your axion photon conversion begins to become suppressed by that axion mass term, which was in that mixing Hamiltonian. But this weird bump here comes from some cancellations that you get between the axion mass term and the Euler-Heisenberg terms. There's a little bit of non-trivial structure related to the fact that you have those two mass scales floating around in your Hamiltonian. But eventually, as you get to high enough masses, the conversion probability just starts to become suppressed. The other possibility is that you don't couple in the UV to electrons, and you just induce that by loops. And so then your axion electron coupling is down by many orders of magnitude because it's loop induced. And you have to make this decision whether you couple to SU2 or to U1 or in what level. The most pessimistic scenario you can take is the W phobic axion, where you only couple to U1, in which case the limit improves still over current constraints. So here's just the difference between that W phobic, where you only couple to U1, and W philic, where you only couple to SU2 couplings. In reality, I would expect your loop-induced coupling to probably lie somewhere between these two red lines. And these two red lines are, again, the 95% upper limits under these two hypotheses. And just for contrast, this is the proposed limit of the ALPS 2 experiment, which is going in at DAISY. So I think that these limits, this result has pretty important implications for the ALPS 2 experiment. It doesn't mean that they can't see anything. But if they do see something, we can immediately say a lot about the ultraviolet completion of that model. So just to mention a little bit about the systematics that affect this analysis, the systematics are pretty minor at the end of the day. Part of that is because we understand this white dwarf very well, and part of that is because the luminosity scales like the coupling to the 4th power, which means that when you put limits on the coupling, you get to take the 1/4 power of everything. And so any change on the luminosity gets mellowed out by the fact that our luminosity scales so fast with coupling. So just as an example, for our fiducial analysis, we took a 1.22 solar mass white dwarf, 1.38 keV core temperature, which was the most conservative of the possibilities we looked at. The maximum rate, which is plausibly consistent with the data, would come from a 1.29 solar mass white dwarf and a 1.8 keV core temperature, but you can see the limit would barely improve under that assumption. So let me start to conclude by telling you about the future of this search on this search technique. I think we've established that this is kind of an ultra clean channel, and now is the time to take advantage of that. So we would like to propose 400 kiloseconds of time on the Chandra telescope, so an order of magnitude more observation time, which would improve our sensitivity going from red to blue for the loop induced, or red to blue down here for the tree level coupling. That is an incremental increase in sensitivity, essentially because the reason I just said, the luminosity scales like the 4th power of the axion coupling. But in the future, we might be able to get more substantial increases in sensitivity. So this is the sensitivity we would get with 400 kiloseconds of this proposed Lynx telescope, which is the Chandra follow-up, which would really be a game-changing telescope, I think, and the sensitivity we could achieve, and would actually get us pretty close to the QCD axion. It would start to bring us close to that territory at high axion masses, at which point I think that begs the question, what would need to be done to bring this all the way down to the QCD axion? So there's the possibility that there are better targets. Maybe this was not the best white dwarf to be looking at. Maybe this is not the best instrument to be using. Or maybe we just need to do the modeling better. So we've just assumed a dipole magnetic field, which is what the magnetic field follows at large distances away from the white dwarf. But close to the white dwarf, it's known that there are higher harmonic contributions, which bring in additional structure and momentum space, structure in K, and then the axion can scatter off of that structure in K, and we know that that can push these sensitivities up to higher masses. And so I think it would be interesting to try to model that magnetic field structure at higher spatial resolution to see if our sensitivity actually isn't better than we think it is at the moment at higher axion masses. So let me just conclude more by telling you about some other future work and work in progress. So first, let me bring us back to this Magnificent Seven story. So how do we reconcile the fact that we saw a signal in neutron stars and we didn't see one in white dwarfs? So these are different channels. One is an axion-Nucleon coupling and the other is an axion-electron coupling. But from these results, we can infer that we need the axion-electron coupling to be about 1/10 of the axion-Nucleon coupling. And these are dimensionless numbers. So I would say this would be surprising in my opinion. It's of course possible because we don't know what the UV theory is, but it's not the first thing maybe you would think of. I would have personally, my belief in this Magnificent Seven anomaly being due to axions went down when we got this white dwarf data, although it's still possible to construct a model, but you have to satisfy this requirement. But I think that brings in a bunch of questions. And these are questions I would encourage people to think about. Can there be alternate processes going on inside the neutron star which dominate the axion rate? So one thing I'm working on right now is looking at muon and proton cyclotron production. We have a muon or a proton inside your neutron star curving around in the magnetic field, the internal B field, and then emitting axions. And it seems like this could actually produce the dominant axion flux for strong internal magnetic fields. But are there other contributions? Can you have contributions off of exotic matter that we suspect exists inside of neutron stars? such as off of pion and kaon condensates? Can we take advantage of flavor changing processes? What about production somehow off of the core gluon plasma? So I think there's more work that needs to be done to see if there couldn't be more exotic mechanisms going on inside of the neutron stars, which couldn't help alleviate this tension by essentially bringing this parameter space down to lower and lower couplings. Another work in progress that I just want to mention briefly using these same magnetic white dwarfs is to use the fact that in addition to converting axions to photons, we can convert photons to axions. And by the non-observation of those axions, you can infer their existence. So this is an idea which actually dates back a decade or so, but we're trying to revive in some work that we should be finishing soon, where we look at unpolarized visible light emitting from the surface of these same white dwarfs. They hit this magnetic field, the photons convert, polarized parallel to the magnetic field, convert to axions, which for an observer at the Earth has effectively given a linear polarization to the light. And so by looking at linear polarization of magnetic white dwarfs, as was outlined in this paper, you can constrain the axion photon coupling. So we're improving the search by using improved modeling and by most importantly, using dedicated polarization data towards the optimal white dwarf targets. And roughly speaking, we expect our limit to look something like what I've sketched here in blue. The actual limit I'm not showing you here, but should be coming out soon. This is still preliminary, but this should also be a substantial increase in the axion photon coupling constraint, essentially without any ultraviolet assumptions about couplings to matter. So to conclude, I told you about these searches for white dwarfs and neutron stars with X-rays to look for axions. I went over data from the Magnificent Seven, neutron stars, and this recent data from white dwarfs. And just to reiterate, ongoing work that we're doing and work I would like to see happen more broadly, we're doing this work on polarization studies from white dwarfs and also neutron stars, which I think will have improved sensitivity. I think it's important to acquire more data towards more white dwarfs and towards more neutron stars, and to acquire more data towards the existing white dwarfs that we've already taken data from. And I just want to open up this question to people to think about, can axions or other BSM explain this Magnificent Seven neutron star excess and be consistent with this white dwarf constraint? So what are ways of enhancing the axion production inside of these neutron stars? Can you have other BSM physics which can do something similar but not show up in these white dwarf searches? I think this is an interesting line of thinking. So thanks.
Well, thank you very much. I'm clapping on behalf of everyone. And well, if anyone has questions, please raise your hand, or well, just ask directly if you don't know how to raise your hand. So we have Filippo.
Yeah, let me start with, so I missed how many sigma is the action explanation of the Magnificent Seven preferred over known astrophysics, whatever. I guess it depends on what you put in known astrophysics, but I'll let you elaborate. Yeah.
The statistical significance is absurdly high. It's over 5 sigma. It's about 5 sigma, a little bit over.
Yeah, because I mean, it looked really like your black dots were following. I mean, you must have been super excited, no, when you saw those plots.
Yeah. I mean, I should say that there are nuisance parameters which go into that model prediction. So it's not quite as rosy of a picture as it would be if there were no nuisance parameters. So we don't know the core temperature of any of these precisely. We have inferences of the core temperature, but we have nuisance parameters. So yeah, we were super excited, but I'm just saying there are still nuisance parameters that make this look a little bit better than how it could be if things were better understood. But we were super excited, yeah, and still are super excited about this, just confused. But the statistical significance is absurd. It's over 5 sigma. But I think that's actually not, yeah, that's, in these astrophysical contexts, the statistical significance can be a bit of a misleading thing to attach yourself to. So there are other concerns here. the two big concerns are instrumental systematics, other complications with data analysis, and then astrophysical backgrounds. So what is another complication with data analysis? Well, when you look up at the sky, you're never sure that you're seeing exactly the thing that you're looking at and not something behind the thing you're looking at. So that's why it was really helpful to have data from Chandra, because we could be sure we were actually looking at this neutron star and not some other source which happened to be photobombing our image. Some of these cameras suffer from pileup, where you can have two low energy X-rays hit at the same time and reconstruct as a high energy X-ray. But we did detector simulations to try to convince ourselves that that wasn't playing a role here. And we believe that that's not playing a role here, but that's always a worry at the back of our minds. And then there's astrophysics. So we don't know of an astrophysical explanation. And since we put this paper, the data paper out a year and a half ago, there's no astrophysics explanation has been thought of yet. But that doesn't mean that one doesn't exist. It's just there isn't one at present. So there are a lot of unknowns that go into interpreting this data.
Thanks.
Yeah. So waiting for other questions, maybe I'll ask, well, let's say one in two parts or two separate questions. The first one is about abracadabra/DM radio. I was curious to know what are the parameters for the GATT upgrade in terms of size, magnetic field, temperature, and time scale. And the other one was on the links follow-up on Chandra. Also there, I'm curious to know about time scales. Thanks.
Yeah, so we're pretty careful not to quote the exact dimensions of this gut, which is why it's convenient to call it gut, because you don't have to put something like meter cubed. So the 50 liter and the meter cubed versions of these experiments are on pretty solid experimental footing at the moment, and that we know precisely what parameters we're going to be taking. I don't have them all off. I don't remember precisely what the magnetic field strengths are, but we know them. They're written down in some science document, and everything is being simulated pretty precisely. Gut is multi-meter. I don't remember exactly if that's 2 meters or 3 meters. It's off the top of my head, but it's on the order of 2 or 3 meters is what we'd expect it to be. And magnetic fields a little bit below 10 Tesla, I think, is what went into this prediction, although don't quote me on that. But the parameters here aren't finalized by any means. Whereas these are, we're at the level of thinking about construction for both the meter cubed detector and the 50 liter detector. So the gut detector could still certainly change around depending on what we see when we run these two smaller experiments. But that's the order of magnitude. And then, yeah, good. Your other question was about this links. This might actually happen on a sooner timescale. We're doing this right now. So first results from this 50 liter and meter cubed experiment. I don't, again, want to quote a time, but that's happening. Links is a bit of a farther in the future. If it's not approved at present, I think the timescale would be 1 or 2 decades from now. If it ends up being the telescope that gets, I'm just trying to get back here. If it ends up being the telescope that gets approved, maybe mid 2030s would be the right time scale, if I'm remembering correctly. Although again, it's still in this early stage of trying to figure out exactly what the Chandra follow-up is going to be. There's going to be one, there's going to be many, and maybe it'll be this one, and maybe it'll be something else, or maybe there'll be 2, one from Europe, one from the US, who knows? But I think this is kind of the right level of sensitivity to be talking about for a future Chandra telescope. Although the other thing to mention is that, I could design a telescope that does this plot better. So Lynx was not optimized for this search. And there's a decade and a half at least until that thing goes up into the sky. So I think it's worth thinking about what would we like to see in a telescope to optimize the sort of physics that we care about, because these things are still in the planning stages.
Thank you very much. So yeah, I mean, this is exactly what I was asking about for links, and well, for the abracadabra GAT, you know that we have some ideas with SRF cavities that could be complementary to your meter cube, meaning we get to the QCD line just below. So I was curious to know how much we should worry in terms of times and money and feasibility, et cetera, et cetera. But so thanks.
Yeah, I mean, yeah, I think that the more efforts which take place here, the better. It's good for everybody. It's good for physics. Yeah.
So do we have more questions?
Maybe I have another one. So still about this magnificent 7 excess. So you say, if one really wants to insist on it, let's think, and one doesn't buy the factor of 10 ratio between electron and nucleon coupling, one could think of new sources of axions in a neutron star. Is there, and this is my question, what I'm going to ask, is there any way that the limit from the white dwarf could have some problem? I mean, have you thought about possibilities for that to be problematic? I don't have anything in mind. I'm just, exploring logical possibilities.
Yeah, we thought quite hard about that, because we really wanted there to be a problem with that white dwarf analysis. And it's really hard to see where it could be. I mean, we spent about a month making sure we were looking at the right part of the image, because it's very scary to open up a blank image and just say, oh, it's there at this blank spot in this blank image, because you're always worried that you didn't do your astrometric calibration correctly, or because the image was just completely blank. But what we did to kind of convince ourselves that we were calibrating the astrometry correctly was to identify other sources, X-ray sources in that image, and to match them on to their Gaia location. So we could, in that astrometric calibration process, we shifted the image around, and it just fit perfectly like a puzzle, matching known X-ray sources with Gaia sources. On the modeling side, I mean, the magnetic field, you could say, oh, how well do you really know the magnetic field? But it's Zeeman splitting. So it's this very straightforward thing of looking for lines being separated as a function of magnetic field strength. And and the other thing is there's a redundancy on everything. Like, we also have this independent way of measuring magnetic field from polarization, circular polarization. And then with the core temperature, there again isn't that much wiggle room there, because the core temperature is tied up with the white dwarf luminosity relation. So all of this modeling is very well determined by data from other white dwarfs. And I guess going along with that, you could say maybe you're not doing the calculation correctly. Maybe you're messing up this ionic form factor, because that involves some numerical lattice calculations. The tricky thing there, though, is that people really care about these calculations, because the same ionic correlation effects affect the neutrino luminosity, which is the luminosity which drives white dwarf cooling at early stages. And so the neutrino luminosities are very well determined by fitting the white dwarf luminosity relation. So essentially, you can just take the neutrino luminosity formulas and rescale them and end up with the axion luminosity formulas. And the neutrino luminosity formulas match extremely well to data. So yeah, it's hard to see where this would fail. Whereas in the neutron star case, I can see many places along the line where it could fail. The white dwarf case, it's really hard to try to find an issue for a vanilla QCD, for a vanilla axion.
Okay, thanks.
Yeah.
Thanks. I look forward then to more neutron star papers by your group then.
Yeah, thanks.